Alright, I'm going to start the lecture notes for LT2 covalent bonding. We are in Unit 4, which is the bonding unit. This is the notes guide if you would like to use it. Otherwise, you can just use a piece of paper. It is Chapter 8, Section 1, if you'd like to follow along in your textbook. Alright, so the first thing that is on the notes that you do need to think about with bonding is why atoms bond to begin with. Atoms are going to bond so that they gain stability by sharing electrons in a covalent bond. If you recall back in ionic bonds, electrons were transferred from the metal to the nonmetal and ions were formed. But in covalent bonding, electrons are shared between nonmetals. They do this so that they have a full outer energy level. Covalent bond is a vocabulary term you're going to need to know. It is a chemical bond that results from sharing electrons in a non-ionic compound. So non-ionic essentially means covalent, but you might see that phrase, a non-ionic compound. It's always between two nonmetals, and an example could be like F2, where fluorine shares 2 electrons to become F2. A molecule is a term that is used with covalent compounds. The smallest unit of a covalent compound is referred to as a molecule. It's formed when 2 or more atoms bond covalently. So you have to have a covalent substance to use the term molecule. This is a water molecule. These are both nonmetals. This is a glucose molecule. These are all nonmetals. The smallest part of an ionic substance, such as NaCl, is called a formula unit, or potassium iodide. That's called a formula unit, the smallest part of it. But the smallest part of a covalent substance is called a molecule. So the smallest thing you can have of water is a water molecule for it to still retain the properties of water. Diatomic molecules are di, meaning two atoms that have a covalent bond. So there are different diatomic molecules. Here are all of your diatomic molecules, and what that means is that in nature you'll never just have a single hydrogen atom or a single oxygen atom. They'll always be in pairs. Now, why is that? These 2 molecule atoms are more stable than the individual atoms. H by itself has 1 valence electron. It's not stable. But when you bond 2 H's together, now you have a stable molecule. Same thing for oxygen. It has 6, 2 valence that need pairs. When you bond them together, it forms a double bond, and you have a more stable molecule. A good way to remember your molecules is the mnemonic Hofbrinkel. Hofbrinkel will help you to remember hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Those are all the elements that are found in pairs in nature. They're never found alone. Now, if you're talking about CO2, CO2 is a molecule that's bound together. The O2 is not because it's a diatomic molecule. Or H2O. That's water. It's a water molecule. It's not H2 because it's diatomic. It's only when these are on their own, when they're by themselves. When we start writing equations and you have like hydrogen reacts with oxygen, that's a good example of where you would have H2 plus O2, not H plus O. There is no H plus O. That would be them being in their singular form, and that doesn't exist. The formation of a covalent compound can be depicted with using Lewis dot structures, just like an ionic compound. However, instead of having arrows of electrons being transferred, instead they're being shared. So you can circle them or you can put them in the middle, showing that they're being shared. These are called shared electrons. This dash represents 2 electrons, and those are shared electrons. The rest of these are called unshared pairs, unshared electrons, or they're called lone pairs. Remember, you know how many valence electrons an element has by looking at the group number, and then any singles will have to be paired up. However, the electrons are already paired, you don't bother. There are 3 types of covalent bonds, single, double, and triple. A single has 2 electrons or 1 pair between 2 atoms. It's the simplest kind of covalent bond. A double covalent bond has 2 pairs or 4 electrons shared between 2 atoms, and a triple has 3 pairs or 6 electrons shared between 2 atoms. Bond length and strength have an inverse or an indirect relationship. What does that mean? That means the longer the bond, this is a long bond, 154, versus a short bond at 120. The longer the bond, the less energy it takes to break it. This long bond takes 345 kilojoules per mole. This short bond takes 835 kilojoules per mole. So the longer the bond, the less energy it takes to break it. So that's called an inverse relationship. As one goes up, the other goes down. The more bonds you add, the shorter it gets. You can see a single bond versus a double versus a triple. It gets shorter. And as it gets shorter, it gets stronger. Okay, so in the lab, we talked about how as you increase bond number, the energy goes up. That's a direct relationship. But as you increase bond number, the length goes down, and that's an indirect relationship. These are also indirect, energy and length. So you have to kind of think about it in your brain a little bit if it's a direct or an indirect. All right, energy and bonds. This is where we're going to start the section on what's called enthalpy, or the energy transfer in a reaction. Now, we've talked about this. Breaking a bond is going to take energy or require energy to be put in. That's called an endothermic, therm meaning heat or energy, endo, into. It's an endothermic process, like breaking a pencil. However, making a bond will release energy. That's an exothermic process. So when you're just looking at those individually, breaking bonds requires it, making bonds releases it. But we have to look at it in terms of a whole reaction. So if you look at this picture, here are your reactants and here are your products. Your Y is energy, your X is the reaction progress. So when you look at this reaction, you're going from reactants up to products. So if this is your energy, you can see the reactants have less energy than the products. So in order to get up to the products, you have to absorb energy to get up there. All right, so here it is written out in words like from the textbook. It takes more energy to break these bonds than is released when these bonds form. Greater energy is required to break the bonds in the reactants than is released when the new bonds form in the products. So where is all that energy? It's stored in the bonds of the products. So one more time, think about it like, okay, my reactants are simple, my products are complex. So in order to go from a simple reactant to a complex product, energy is needed to get there. You can't get to something more complex, bonds that have more complex energy, unless energy is put in. That's endothermic. Here's a nice example. CO2 is a simple molecule, water is a simple molecule, and it makes glucose in this process of photosynthesis. Glucose is a very complex molecule. There's a lot of energy stored in these bonds. So how do we get from simple to complex? Light. Energy had to be put in to the process. It's an endothermic process so that we could get the energy stored in these bonds. Exothermic processes are just the opposite. Your reactants have high energy, your products have low energy. So the extra, the leftover, is given off as heat. It's like a ball rolling down a hill. It releases the energy. Exothermic, less energy is required to break the bonds in the reactants than is released when new bonds form in the products. So let's go back here and look. Less energy is needed to break these than is released when the products form. An easy way to think about it is complex to simple. I have a lot of energy stored up in the bonds of my reactants. I have little energy stored in the bonds of my products, so the extra, the leftover, has to be released as heat. Reactants have more energy than products. Think, more complex reactants make simpler products, so the extra is released as heat. A good example for this would be like burning gasoline in your car. When you burn gasoline in your car, you have gasoline, which is a complex molecule. Here's your gasoline. And of course it has to have activation energy, something to start that reaction or start that burning process. But then once it starts burning, this is your water and your CO2. And those are less complex products. So your extra is when your engine heats up. So complex to simple, you've got to have an energy release, which is exothermic. Here's an example of an exothermic graph. Complex reactant, simpler products. So after the activation energy is, after you have the amount of activation energy needed to start the reaction, then as these products form, the extra energy left over is given off as heat. Take a look at these two graphs and think which one would be an endothermic graph. I hope that you picked B. You have simple reactants and a more complex product. You also have your reactants having less energy or enthalpy. Enthalpy is just a word that essentially stands for energy here. And your products have more energy. So to go up to that product, you have to gain energy. And that's what this positive change in H or change in enthalpy means. Positive means it's an endothermic process. Negative means it's an exothermic process, or energy is being released when your CH4, which is more complex, is being burned with O2 and forming CO2 and water. All right, next I want you to fill in the word exothermic or endothermic on question 1, when two chemicals mix and their temperatures rise. All right, so it's getting hotter. So remember, therm means heat or energy, and so exo is exit, endo is into. So if their temperature is rising, is heat being released or absorbed? Hopefully you're thinking released, and it is an exothermic process. So go ahead and do B through E on those. On number 2, during chemical reactions, the bonds between atoms break and new bonds form. Energy must be absorbed to break a bond. So breaking bonds is endothermic. Making bonds is exothermic because energy is released. When this copper carbonate decomposes, here's your equation. I have a little bit better of a picture of it. This is hard for you to see. It's right there. So would that be an endothermic or an exothermic process, and use ideas about bonds? So are we going from complex to simple? Are we going from simple to complex? That's probably the easiest way to think about it. Hopefully you're thinking this looks more complex. There's probably more energy in these bonds than in these smaller molecules. So this would be complex to simple. So that would be an exothermic process. You have more energy stored in these bonds than are stored in these bonds. So the extra gets released into the environment. It's an exothermic process. The next one, you have to do a little drawing of two hydrogen atoms. I would just use circles like they use, but instead of using colors, unless you have colors, I would just put the letter H in the circles. And then it asks you to mark the bonds broken in blue. You can do that with a blue marker or just with a dashed line. The new bonds in red, or you can just use a solid line. Most reactions involving bond breaking and bond making, the equation shows what happens when methane is burned. Mark the bond broken in blue and bonds formed in red. Again, you can just use dashed lines and solid lines. Your reactants are always going to be, the bonds are always to be broken. You have to break the bonds of the reactants, and then these bonds are formed in the products. It says complete the table showing where bonds are broken and formed between carbon and hydrogen. So here's our CH4. So how many bonds are broken? Well, we have 4. Between the oxygen atoms, well, we had 2. How many bonds are formed between carbon and oxygen? So we have CO2, so we have 2. And you all can see we have 4 there. Is this exo or endo? Think about, are we going from something more complex to less, or less to more? All right, I was running out of time. I want to make sure you see the key. Here's for number 1. Here's for number 2. Here's for number 3. Bottom, and here's for number other side.